Welcome to this new episode of FEA Insight. Today we're going to talk about modeling bolted joints. As you know, mechanical industry has developed technologies to manufacture integrally machined parts, additive material process, friction stir welding, and so on. But even with that, many small and large structures still require the use of bolted joints. Because a mechanical structure is usually made up of many components that can be manufactured from thin shells, extrusions, machined parts, and cast or even forged parts. And to form the structure, these components must be connected together with bolted joints, which are often the weakest points in the structure. So basically, joints make up a large part of a mechanical structure, and they influence the overall structural behavior, and you have to analyze them. So the components can be joined using three different approaches. First, the bolted joint, the welding, but also the bonded joint. The bolted joint is by far the preferred solution for joining two components. However, welds are also intensively used. On the other hand, the bonded joints are used to build composite structure like carbon monolithic, sandwich honeycomb. In those cases, the bonded joints are used. However, this episode will only cover the current state-of-the-art in finite element modeling of bolted joints because, as I said, it is massively used in a mechanical structure to join components together. So, before to jump into the details of this presentation, this episode, let me presenting you the agenda of this episode. I want to start with a refresher about bolt behaviors and also answering the question, do you really need to model the bolts? Then I'm going to cover three methods in order to model the fasteners, the bolted joints. First, the rigid elements, the 1D spring elements, and the beam elements. Then we're going to talk about how to calculate the stiffness of the fasteners, of the bolts, when they are modeled with 1D springs. And finally, I'm going to conclude this episode by answering the question and showing you example of how to connect the fasteners to the surrounding mesh. It's a very important question since when you model the fasteners, you need to connect them with the surrounding mesh. So before to go to the modeling techniques, I want to present quickly the typical bolt behaviors. To conduct a correct structural analysis, it is important to understand how the structural parts interact and transfer load through mechanically bolted joints. Large structures generally exhibit large in-service forces, which make bolted joints deform to accommodate the transfer load. So the behavior of bolted joints is very complex because fasteners can exhibit different types of loading. In fact, the shear loaded joints are subjected to primary bending, secondary bending, and local bending of fasteners. Okay? So in summary, the primary bending is due to a bending moment applied at the ends of the joint parts, while the secondary bending is due to a tensile or compressive force acting in different planes in the case of eccentricity. And the local bending of fastener is a typical bending of the fastener due to opposite shear loads. So bolted joints are difficult to analyze because many parameters and complex phenomena are involved in the joint's behavior. We have the plate bending, the fastener bending, the bolt hole deformation, the friction effect, the preload on the fasteners, and contacts. So it is impossible to consider all these parameters in the structural analysis of a bolted joint. Okay, so it is necessary to reduce the problem by making assumptions and applying modeling rules. So it is also important to mention that a few years ago, analyzing a joint was problematic for the finite element process. In terms of modeling time, because each fastener has to be modeled by one or several elements. Okay? However, with the modern FEA packages, the process is much easier and we can now model each fastener rapidly in a complex joint. And I'm going to show you how we can do that. So the first question you have to answer is, do you really need to model the bolts? And this is a typical question you should ask yourself when you plan to model the bolts in an FEM. First, it is important to mention that modeling the bolt in structural analysis does not mean that we model the bolt with the head, the nut, and the washer with a 3D model. In structural analysis, the objective is not to design the bolt. It is to capture the load transferring through the joint, the shear force, the axial force, and the bending moments. So the bolts are discretized using MPC or 1D elements with their representative stiffnesses. The loads in shear and tension captured with the FEM are used to verify if the bolts and the assembled parts can withstand the loads. And this check is very basic, okay? Because it is a very basic end calculation done using the bolt loads extracted from the FEM. So it is very important to accurately representing the stiffness of the joint in your FEM. And we will see how to do that in the next slides. When you are preparing to include a bolted joint in your FEM, you must ask and answer the following questions. The first one is, do you want to capture the load transferring through the joint? Do you want to account for the preload? And do you have to design the bolt? So if you answer yes to any of the above questions, you must model the bolts. If the answer is no, do not waste your time. Instead, join the parts with a node-to-node approach, and it is very efficient. In fact, even if two parts are mechanically attached using fastener, you may not be interested in the loads transferring through the joints in the preliminary analysis. In that case, you can create a global model of your structure without including the bolts by joining the parts with the node-to-node technique, meaning that the parts are connected with coincident nodes. With this type of model, you will be able to represent the stiffness of your structure properly and accurately predict the deformations and distribution of internal loads in the different components of the structure for a large number of loading conditions. The advantage of the node-to-node approach during the preliminary study is that it is easier to iterate on the structural solutions, since you don't need to manage the connections between the components with additional elements. You only need to ensure that there is mesh continuity between the connected parts at the preliminary stage. When the design of the structure is mature, and after a few iterations using your global model, you can start to consider modeling the bolts to capture the load transferring through the joint and investigate its detailed behavior. Bolts can be added in the global model, in that case, from this stage, using a refinement technique or a submodeling approach. Modeling each board will permit you to accurately answer the three following questions. Will the parts remain assembled when subjected to the external load? What will break first, the bolt or the connected parts? And can the joint parts sustain the repeated load? So let's see what are the typical FEA modeling approaches for bolted joints. Very different methods are used for the finite element modeling of bolted joints. First, the joint parts can be modeled with shell or solid elements. It depends on the nature of your model. It depends on the assumptions you did at the very beginning when you measure your model, when you create the model. So the modeling techniques we will discuss in the next slides can be applied with parts modeled in 2D or 3D. For both shell and solid models, the bolt element is a link between the nodes belonging to each of the parts to be joined. The load distribution in the joint depends on the geometrical and material properties of the joint parts, but also on the stiffness of the fasteners connecting the parts. So the accuracy of the joint analysis is highly influenced by the fastener modeling technique. The common techniques used to model bolts in a FEM are the rigid elements, the discrete spring elements, the beam elements, and a combination of rigid discrete springs and beams. It is known as the Rootman approach. I will not cover the Rootman approach in this lecture. So let's see these three first modeling techniques in detail with their advantages and disadvantages. The first one, it is the bolt model with the rigid elements. These modeling techniques permits for the representation of fasteners as rigid links of infinite stiffness. It uses the famous RB2 elements in the Nastran word, or SERIG in the ANSYS word, or the kinematic coupling in the Abacus word. There are advantages using those rigid elements in order to model the bolts or the fasteners. The first advantage, it is the fact the analyst does not need to know the properties of the fastener, like the diameter, the material, etc. And no stiffness calculation is required for the joint. The analyst can choose the transferred degrees of freedom also that the rigid element can transmit. It is a huge advantage. For example, the analyst can decide to transfer only the shear, okay, or only the axial, and not the moment, for example. So the rigid elements are versatile, so they permit this choice. But there are also disadvantages using the rigid elements in order to model a bolt. The first one, it is the fact that the stiffness of the fasteners is highly overestimated compared to their roll stiffness. Consequently, the displacement of the fastener along with the bearing behavior around the fasteners will be incorrect. So you can use this modeling technique if you want to capture an effect far from the region of the joint. But you need to connect two parts in order to have the correct load path. But your zone of interest is far from the region of the joint. Okay? But you cannot use this modeling technique if you must accurately capture the joint displacement or the joint loads. Keep in mind that 75% of the joint's overall displacement is a direct result of the fastener's displacement. The second modeling technique that you can use in order to represent a board, a fastener, is the discrete spring element. This one is the most used method for modeling bolt joints. The discrete spring element is a 1D element having 6 degrees of freedom corresponding to the following capabilities of the board: the axial capability, the shear in 2 directions, the bending in 2 planes, and the torsion, usually very low. The discrete spring element is located in the model at the exact location of the fastener in the space. And this 1D spring element joins the 2 nodes belonging to each of the parts to be attached. And the stiffness corresponding to each degree of freedom is calculated using semi-empirical relationships. So let's see the advantages of modeling fasteners using discrete 1D spring elements. First, the modeling technique is accurate and give representative results because the correct fastener stiffness is represented. Okay? And the deflection of the fastener is properly captured. Again, because you enter into the model the exact stiffness of the joint. The disadvantages of this approach, it is the fact that the analyst has to calculate the stiffness for each fastener. And the mesh of the parts connected by the spring element must be adjusted to connect the spring element realistically. And after this, later in this presentation, I'm going to show you how you can do that. So when do you use this modeling technique, the 1D spring element? You use it if you want to capture the load transferring through the joint. Remember that with the previous method, the rigid element, you cannot capture the load transferring through the joint. But here you can. So if you need to evaluate the load transferring through the joint, you have to use this modeling technique. But you cannot use this modeling technique if you don't know the mechanical properties and the diameter of the board. Okay? Because if you don't know that, you won't be able to calculate the stiffnesses. So when a joint is modeled using this 1D discrete spring approach, you are responsible as the analyst, you are responsible for the calculation of the fastener stiffness. The discrete spring element has no geometrical or material property. So the FEA software cannot calculate the stiffness of the element based on its properties. Keep in mind that when you create you use a shell element, for example, you tell the solver the surface by the mesh, you tell the solver the thickness, the material, so the solver is able to calculate the stiffness. It is not the case for a 1D spring element. Okay, the 1D spring element, you just inform the solver the 2 nodes connecting the spring. So the load transfer between components is greatly influenced by the fastener stiffness. So particular care in the stiffness calculation must be taken to accurately capture the load transferred in the joint. You must first define the degrees of freedom the joint will be able to transfer, and then calculate the associated stiffness. Basically, depending on the joint's configuration, a fastener can transfer the different degrees of freedom. Axial, shear in 2 perpendicular directions, bending in 2 perpendicular planes, and torsion. So let's see how to compute the 1D spring stiffness for a bolt-on joint. Here I want to discuss first the parameters, okay, involved in this calculation. So you see the parameters are the Young modulus of the fastener, the fastener material, the Poisson coefficient for the fastener material, the Young modulus for the two parts connected together, and the shear modulus of the fastener material. The diameter of the fastener and the thickness of the two parts connected together, the distance between the mid-plane of the joint part, like the grip, let's say, the cross-section of the fastener, and the moment of inertia of the fastener. Here, I'm talking about the fastener's chain. So basically, the actual stiffness is very easy to compute, okay? Since it is this equation, I'm pretty sure you already know it. Here, the Young modulus of the fastener, the cross-section of the fastener, and the distance between the two plates is involved in this calculation for the actual stiffness of the joint. Now let's discuss the shear stiffness. There are many equations, empirical equations available in the literature to calculate the shear stiffness, but here I want to present you the three most used method for the shear stiffness. First, the Tate and Rosenfeld method, the Swift method, and the Hutt method. Okay, here those equations gives you the flexibility factor that you can use in order to calculate the flexibility of your fastener. Obviously, the stiffness of the fastener is the 1 over the flexibility. So you see the parameters involved into the calculation of the flexibility. You recognize those values that I discussed in the previous slide here, where you have the Young modulus of the fastener, the Young modulus of the plates, the diameter of the fastener, the Young modulus of the fastener, many parameters, and even in the Hutt method, few empirical factors, you see B1, B2, which are factors depending on the material of the plates. You can have metallic, or even composite and composite metallic plate assembly, and the type of the joint, if it's a bolted joint or a rifted joint. So it is the reason why the Hutt method is one of the most famous methods used to calculate the shear stiffness. Okay. So here on this slide, I want to show you the different shear stiffness obtained with the three methods, the Tate, Rosenfeld, Hutt, and Swift. First, for a plate material aluminum, and then a plate material steel, and with a fastener material titanium, and a fastener material also titanium in this one. So this one, it is a steel titanium, in this one an aluminum titanium. Okay. So you see the variation between Swift and Hutt is significant, while between Tate, Rosenfeld, and Hutt it is closer. By experience, the Hutt formulation is the one used most frequently in many industries. Now for the bending, here are three methods. The first one, it is a calculation depending on the shear stiffness that you calculated before using one of those equations, okay? And depending also on a distance between the plates. Here it is the basic stiffness of the bolt, but also it can be a calibrated value based on test. So the three methods used in the industries, the two first methods are the most common methods used in the industry. The third method used to model bolted joints, a fastener. A fastener can be modeled also using a beam element connecting the two nodes with 6 degrees of freedom per node belonging to each of the parts to be joined. Okay? As with the discrete spring element, the beam element is located at the exact position of the fastener in the model. Okay? Like the 1D spring element, the two nodes located on each component must be perfectly aligned with the position of the fastener. The advantages of this approach is the fact that the correct fastener stiffness is represented and the deflection of the fastener is properly captured. And another advantage is the analyst does not need to calculate the fastener stiffness. The reason why is because you model the fastener with the beam element, and the beam element contains all the information to permit the solver computing the stiffness, because you enter the beam elements with the characteristic, the cross section, the moment of inertia, the material. Okay, so the solver is able to calculate the stiffnesses directly. The disadvantages, it is the fact that the mesh of the parts connected by the beam element must be adjusted to connect the beam element realistically. So you can use this modeling technique if you want to capture the load transferring through a joint, okay? But you don't use this modeling technique if you don't know the mechanical properties and the diameter of the bolt, because you won't be able to define the beam element if you don't know those properties and characteristics of the bolt. So here, to conclude with this, the presentation of the modeling approaches for the bolted joints, I want to discuss a few points. To properly capture the distribution of loads in a bolted joint, the correct stiffness of the joints must be accurately represented. And it is the key point here, the correct stiffness of the joints. Okay, and Brian Kitt and Chris Boschers from Spirit Aerosystems demonstrated that the elastic spring elements modeling techniques predict results that are in agreement with the experimental data. You can read those conclusions in this paper, Verification of Fastener Modeling Techniques for Joining Composite and Metallic Assembly, in the series of the SAE International in 2010. So it is a very important result, because they did many tests and many correlation, I should say, between test and modeling using the techniques I presented before. So it's a very important result. So I repeat that they demonstrated that the elastic 1D spring elements modeling technique predict very accurate result against experimental data. On the other hand, they demonstrated also that the bar element representation over predicts a little bit the fastener load, but not as dramatically as the rigid element method, for sure. So keep that in mind. The rigid element method is really a preliminary method when you want to evaluate how the internal loads are distributed between the parts, okay? And you are not interested with the load transferring through the joints. So now the question is, and this will conclude this presentation, this episode, how to connect the fastener elements to the surrounding mesh, okay? Because even if we model with 1D spring element or 1D beam element, we need to connect those elements with the surrounding mesh. So two situations can occur. The first one, it is when the fastener hole is modeled, and the second one is when the fastener hole is not modeled. Okay, it depends already on the assumptions you did when you build your model at the very beginning. And it is not important if it's 1D or 3D, because it is the same approach. So here in this example, I want to cover first how to connect the bolt element when the hole is modeled. So here you see, for example, you have two plates modeled with holes. The yellow plate here and the red plate. In this example, they are modeled with 2D shell element, okay? But what I'm going to present you here can be applied also for a 3D solid mesh. So here it is an exploded view showing a bolt, okay, between the two plates from this node to this node. So now the question is, how do we connect the extremities of the bolt, 1D spring on 1D beam element, to the surrounding mesh? So first, here it is the technique we use in order to connect. Here you see the shell element, let's say the plates viewed from the top, okay? And here in the middle, it is the node where the 1D beam element or 1D spring element arrive. So first, you have to connect the beam element or the 1D spring element using an interpolation element, which is a multi-point constraint element, an MPC element, and it is a R-type interpolation element. You can see that in my course, in my practical basic course, where I have a lecture about the MPC element and the R-type element. So it is an interpolation element, okay? And you connect this interpolation element with the inner layer node of the hole. And the center node is the dependent node and the degrees of freedom of the 6 degrees of freedom. And the inner layer nodes are the independent degrees of freedom. And you, in that case, you specify the translational degrees of freedom. Then you have to connect also the outer layer nodes, but with a rigid element. So again, the center node is now the independent, since it's a rigid element, and you connect the outer layer node, which are the dependent nodes, and you specify only the out of plane translational degree of freedom. Here I name it 3 because if you come back here, the orientation of the joint is like that. So the shear plane, it is the plane XY, and the actual axis, it is the Z plane, the Z axis. So it is the reason why here in my case the out of plane translational degree of freedom, it is the degree of freedom number 3. Okay, so here you see the names of the rigid and interpolation element that you can use depending on the solver you are using, Nasren, ANSYS, or Abacus. So due to high stresses at the rigid and mesh connections, especially here due to in the out of plane degree of freedom, it is standard practice to neglect the stresses in the washer region and one more layer surrounding the connection, okay? Because here you are going to have an excessive stiffness due to the rigid element. But the load that you are going to capture into your bolt or your 1D spring or 1D beam element will be correct. The behavior of your joint will be correct. Here it is an illustration with a 3D approach. You see it is the same, except that the MPC element are in 3D. So you have a node here, another one here at the middle of the two holes, connected with a 1D spring or a 1D beam element. So the two parts can be TET or X-meshed. It is the same approach. So now let's see the other situation where we connect two parts where the hole is not modeled. Okay, so here you see those two parts in blue a stiffener, in red a plate, and you have discrete bolts here, and you want to connect the stiffener to the panel with 1D elements because you want to capture the loads in each bolt, and you want to predict with your model how the load is going to be distributed between the different bolts. Okay? So first, the first method, it is a method connecting 1D element with congruent nodes. By congruent nodes, it means that you install the 1D element between two aligned nodes. So it means that when you created the mesh, you already manage the location of the fasteners, and you forced the mesh to pass at the exact location where you have the fasteners. The result of this management, it is the fact that you're going to have two nodes on each part aligned with the location of the bolt. Okay, so at the end, it will be very easy to create a 1D element connecting directly the two nodes, one node stiffener side and another node mesh side. This is the first method. It is the method of the congruent nodes. So keep in mind, in order to apply this method, you absolutely need to know when you create the mesh, where are the bolts. And if you change the location of the bolts, you will have to adjust the mesh in order to make sure that the nodes are aligned with the new location of the bolt. The second method, it is a method using interpolation elements. And in that case, when you create the mesh, you don't need to know the location of the bolts. Okay? Why? Because as you can see on the left, you see here the green line, it is the location of the bolt. The bolt arrives here in the panel. And you see there is no mesh nodes panel side. So what you're going to do, you are going to connect the 1D element to the mesh of the panel using interpolation element. So here I use at least 4 nodes, okay, in order to represent properly the head or the washer of the bolt. Okay. On the other end, it is the same. On the stiffener side in blue, my node here of the bolt is not aligned with a node of the stiffener, of the mesh stiffener. So I use an interpolation element, okay, which is a typical MPC, usually an RBA3 or a coupling element for abacus. So the advantage of using those elements, it is the fact that they don't those elements, they don't add any stiffness into the system because they are interpolation elements. If you want to know more about those interpolation elements, as I said, I have a lecture in my Practical Basic FEA course covering in detail how those elements are working. So you see, using this method, you have more flexibility if you want to change the location of the bolts. Because when you change the location of the bolts with this method, you don't need to remesh or to manage the mesh of the two parts connected with the bolt. You just manage the interpolation elements. And in the modern pre-processing software, creating those interpolation elements, it's completely automatic. Okay, so it's very easy when you change the location of the bolts to reconnect them with the surrounding mesh. So that's it for this presentation. I hope that you learn a new thing about how to model bolted joint. You can find those information and many more information about bolted joint in Practical Finite Element Analysis for Mechanical Engineers, available on the FEA Academy website. But also, you can see those courses, the practical basic finite element analysis and the practical nonlinear finite element analysis online courses on demand, pre-recorded courses where you can learn many other modeling techniques for building reliable and accurate finite element analysis model. Thank you very much for watching, and I see you in another episode of FEA Insight.